Hi everyone! Today let's talk about section 4.3, the geometric and hypergeometric distribution. In section 4.2, we studied the probability of k success in n trials. What happens if we want to find the number of trials until the first success? How many independent trials until the first success? So given the probability of each success is p, then the probability of the first success in the cave trial is, okay, so here the picture is like that. So this is the cave trial. And all those previous trials, we have failures. And we have success in the last trial. So that's why we have 1 minus b. That is the probability of failure. And we have k minus 1 failure times the last one is success, so that's p. Okay, so we have k minus 1 failures and 1 success, and then this is the probability. Remark, this experiment has infinitely many outcomes and potentially infinitely many trials. So unlike our binomial distribution in section 4.2, we have the number of trials is fixed, and then the number of success varies. Okay, but right now, if we're looking for the first success in the cave trials, we have the number of trials varies, and the number of success is fixed, which is 1. Okay, and so let p be a probability between 0 and 1, and it cannot be 0 because we're talking about the first success in the cave trial. So the probability of success must not be 0. So we need to have at least 1 success, right? Okay, random variable x with range. This means the range of x is a subset of the natural numbers. Okay, so that's why natural numbers can be 1, 2, 3, okay? And g of kp equals the probability mass function p x equals to k, and that equals 1 minus p to the k minus 1 times p for all k in the natural numbers. And then this random variable x with the probability mass function has the geometric distribution with success parameter p, and we denote x has the geometric distribution with the parameter p. Okay, so again, remember, to prove a function is a probability mass function, we need to show, okay, so for PMF, we need to show first the function is greater or equal to 0. And you can see this guy is greater or equal to 0, right? 1 minus p is positive, and p is positive. And also, we also want to check the sum for all the p of x equals 1. Okay? So in order to check this, we need to recall some knowledge in Calculus 2. The geometric sequence is the sequence with the terms a0, a1, where ak equals a0 times r to the k. So a0 is the initial term, r is the ratio. Okay, and then the nth partial sum of geometric series is Sn. Sn is the sum of the first n terms. Okay, so I from 0 to n. Oh, actually, here we have n plus 1 terms. Okay, and this equals sum I from 0 to n, a0 r to the I. And we can pull the a0 outside of the sum. And then now we get this guy. So what is this guy? This guy is actually equal to 1 minus r to the n plus 1 over 1 minus r. Why is that? Let me show you. Okay, so let's call this guy s. So s equals 1 plus r squared plus plus r to the n. Okay, now what I'm gonna do, I multiply both sides by r. Then we have r times s. 1 times r is r. r times r squared. And then we have r to the n plus r to the n plus 1. Okay, now what I'm gonna do, I use the first equation, subtract the second equation. And then on the left-hand side, we get s minus r times s. So we can factor out s, we get 1 minus r. And on the right-hand side, you can see r cancel, r squared cancel. So we get 1, and then r to the n cancel. So we get 1 minus r to the n plus 1. So s equals 1 minus r to the n plus 1 over 1 minus r. So that's why we get this formula. Okay, and the geometric series converges if the absolute value of the ratio is less than 1. And because of the exponential function, so this is like the exponential function. If the base is less than 1, then we have the exponential function looks like this. Okay, so this is r to the n when the absolute value of r less than 1. So this is a decreasing function. When n goes to infinity, this guy goes to 0. So that's why the geometric series converges. And I think there's a typo. This is infinity. The series will converge to a0 over 1 minus r. So a0 is like the first term in the series, and then over 1 minus the ratio. Okay, and now let's come back. Okay, let's come back. Now when we add the PMF, I mean this function, okay, let's add this. So when we add k from 1 to infinity, okay, this guy 1 minus p to the k minus 1 times p. What is this? Okay, so now you can see this guy, the first term, when we plug in k equals 1, the first term we get p over 1 minus the ratio. The ratio is 1 minus p. So that's why you get 1 and 1 cancel. We get p over p. This is 1. So that's why you get the sum of all these probability distributions equals 1. So this is in fact probability mass function. Okay. Very good. So now we talk about the geometric distribution. Let's look at example 1. If the probability is 0.05 that a certain kind of measuring device will show excessive drift, what is the probability that the 6th measuring device tested will be the first to show excessive drift? So for geometric distribution, you will see like the order, the first, the 6th. Okay, so this is like the first success in the 6th trial. So that's why this is a geometric distribution. Okay, and here p equals 0.05, right? So now let's see. So p of x equals 6. So here we have failures, 1 minus 0.05. And remember, now we have the 6 boxes. So all the previous 5 boxes are failure, and the last one is success. That's why we have 1 minus 0.05 to the 5th times 0.05. So this is 0.95 to the 5th times 0.05. Okay, let's put this in the calculator. 0.95 to the 5th times 0.05. The answer is 0.03869. We round up, okay? So 0.03869. 0.03869. Okay, so this is the answer of example 1. Okay, example 2. Roll a pair of fair dice repeatedly until the sum is 5 or 7. Find the probability that the sum is 5 on the last row. Okay, so here, let's define the event. Okay, so the last trial is either 5 or 7, the last row, okay? And we don't know how many total trials are there, right? So that's why let's let A and B. We have n trials, okay? So we have n trials. N trials. Why we get n trials? That means the sum is not 5 and 7 in the rows 1, 2, 3 up to n minus 1. And let's say the sum is 5 on the nth trial. Okay? Yes. So now you can see we get a sequence. We get a sequence an, n from 1 to infinity, and all these events, they are pairwise disjoint. And if we take the union of all these events, we get what? We get the event of sum equals 5 on the last row. This is exactly what we want to find, okay? And because here last row, but we don't know how many rows are there, right? Okay, so now let's see. Okay, so what is the probability of sum equals 5 on each row? Well, let's see. We roll a pair of dice. Okay, so we have 2 dice. And then how many outcomes are there? So each dice we can have 6 faces. So the total outcomes is 36. And all the outcomes are equally likely, right? And then we want to think about, okay, how many pair of dice we can get to sum is 5. Okay, we can have the first one is 4, the second one is, the first one is 1, the second one is 4, or the first one is 2, the second one is 3, the first one is 3, the second one is 2, the first one is 4, the second one is 1. And the first one cannot be 5, okay? Otherwise, it's exactly 5. Okay, so here we have 4 outcomes that the sum equals 5 on each row. So that's why 4 over 36, which is 1 over 9. Okay, what is the probability the sum equals 7 on each row? Okay, let's count. We can have 1, 6, 2, then 5, right? 3, 4, 4, 3, 5, 2, 6, 1. So we have 6 outcomes there. So 6 over 36, we get 1 over 6. So far, so good, everyone. Okay, so now what is P of an? So P of an means we have k minus 1 previous row. So here, n minus 1 previous row, sorry. So n minus 1 previous row, and then this guy is the nth row. The nth row, the sum is 5. So the sum is 5, so we get 1 over 9, right? But the previous row, the sum is not 5, not 7. So that's why it's like the complement of the sum is 5 and 7. So we use 1 minus the probability of sum is 5, which is 1 over 9, minus the probability of sum is 7, which is 1 over 6. And then we have n minus 1 over all of that. So that's why we have this guy to the n minus 1. Okay, so 1 minus 1 over 9 minus 1 over 6 to the n minus 1 times 1 over 9. And let's see, what do we get? Well, this guy, the common denominator is 18. And then we have 18 minus 2 minus 3, which is 13 over 18 to the n minus 1 times 1 over 9. So far, so good, everyone. Okay, and then let me erase this because I don't have enough space. Okay, so this is P of an. Now, what is P of a? Because all the an, they are pairwise disjoints. So the addition rule, we can just add the probability of each of them. So that's why it equals sum of n from 1 to infinity, P of an. So that's sum n from 1 to infinity of 13 over 18 to the n minus 1 times 1 over 9. Okay, now this is a geometric sequence, right? Geometric series, and let's see. So that equals the first term. The first term means we plug in n equals 1. So we just get this is 1 times 1 over 9. So the numerator is 1 over 9. And then the denominator, we have 1 minus the ratio. Ratio is 13 over 18. So that's why we have 1 over 9 over 5 over 18. Well, this is 1 over 9 times, so when we divide it by number, it's the same as multiply by its reciprocal. So that's why we cancel. Oh, the answer is 2 over 5. So 2/5 is the answer. Okay, so that's the probability. The sum equals 5 on the last row. Okay, and actually there is another way to solve this problem. Okay, I'm gonna show you here. So method 2. Okay, method 2 is we just look at the last row. Okay, because the last row is either 5 or 7. How many outcomes are there? Okay, so just look at the last row. Here are the possible outcomes. And all outcomes are equally likely. Okay, so that's why the probability, the probability of sum equals 5 on the last row equals, so how many of them the sum is 5? These guy, right? So we have 4 over, what is the total? 4 plus 6. So 4 over 10, which is 2 over 5. You see we have the same answer. Wow. Okay. Well, you might say, wow, we have this quick method. Why don't we use, why do we show the first one, this long process? Because sometimes maybe the second method does not work. And the first one, you can see how we use the geometric distributions, probability to calculate it. Okay, and we also use the geometric series. Okay, very good. Let's continue. And actually, this example is beyond the geometric distribution, because the geometric distribution, each row is either success or failure. And here, the success is sum is 5. But for the n minus 1, the previous n minus 1 trials, the sum is not 5. And the sum is also not 7. So that's why it's not just the failure, but you also have this extra minus 1 over 6. So this example is actually more general than our geometric distribution. So I hope you can like extend this idea through this example. So far so good, everyone. Yeah, sometimes different trials maybe it's not simply just success or failures. There could be more types. Okay, so and then this is a good example to show us. All right, let's continue. When we are dealing with binomial or geometric distribution, the individual trials are independent. So it's like sampling with replacement. What if sampling without replacement? Okay, so remember, if sampling without replacement, the trials are dependent. For example, if we want to pick m balls from an urn containing m green balls and m minus m blue balls. So the urn or the bag only contains 2 types of balls. So it's either green balls, so we have m green balls, or we have n minus m blue balls. Because the total number is n, so that's why n minus m blue balls. So the total number is n. Okay, so we have n minus m blue balls. So let x be the number of green balls we pick. Okay, so let's see here. Oh, by the way, we want to pick n balls from this urn. So we want to find what's the number of green balls pick. Okay, so let m to be less than or equal to n. And it makes sense because n is the total number of balls. M is the number of green balls. So the number of green balls must be less than or equal to the total number of balls. And the small n is less than or equal to n because you want to sample small n balls out of the capital N balls. And we want this n to be smaller or equal to m because we want to allow the possibility that all the balls you sampled, you pick, are green balls. We want to allow this possibility. That's why n is smaller or equal to m. So there are integers, and then a random variable x with range equals 0, 1, 2, up to n. So h, k, semicolon, n, m, n equals the probability x equals to k. Remember here we have k green balls. So that's why here we have total m green balls and we pick k out of it, right? And then we have m minus m blue balls and we pick m minus k out of it. And the total, we have n balls, we want to pick n out of it. So this is the hypergeometric distribution with the parameter n, m, n. And we denote x has the hypergeometric distribution with parameters n, m, n. So in this notation, do you realize n is the largest number? Okay, and m is smaller, and then the small n is the smallest. Okay, but in this notation, you can see n, you put the smallest number first, and then m, and then the capital N. Okay, just different notations. All right, we mark. N here is the sample size. Capital N is the lot size. It's also the population size. And m is the number of successes in the lot. So number of green balls in the urn, okay, for example. All right. So this hypergeometric distribution is very similar to what we have done in chapter 3, right? Okay. So let's look at example 3. A company has 100 identical car chargers, but 25 of them are defective. choose 10 randomly. Find the probability that 2 of the 10 chargers are defective. Part A, use the hypergeometric distribution. Part B, use binomial distribution as approximation. Okay, so part A, use hypergeometric distribution. So we want to figure out the parameters, right? What is the 100? 100 is the population size, so that's 100. 25 of them are defective, so this is the M, okay, like number of success. So in this case, you see, success is defective. So success is not always like good things. It's just like something we are interested in, we want to know about. Okay, so we just call it success, but it could be bad things. So M equals 25, right? And then we want to choose 10 randomly. So small n equals 10. That's our sample size. Okay, find the probability that 2 of the 10 are defective. So probability x equals 2. That is, alright, so we have 25 defectives and we want to pick 2 out of it. Okay, let me ask you, how many non-defective car chargers? So we have 100 minus 25, which is 75 non-defective car chargers. So 75, we choose how many? 8, right? Because the total we want to pick 10, and now we have 2 defective and 8 non-defective. And then the total over, we have 100 chargers, we want to pick 10. Okay, so do you remember how we calculate this? So start with 25, and we count down. So 24 over 2 times 1, and okay, 75. Okay, what is that? 75, 74, 73, 70. Okay, so it looks like this is a long number, right? And 100 choose 10. This is also a long number. Okay, so in this problem, if you see the number is so big, I suggest you use your calculator to compute. Use the combination function. All right, so let's see. Okay, so the online, here I find an online calculator. Here is the website. I found the permutation and combination calculators. So let's see, 25, choose 2. So 25, choose 2. Combination is 300. So 300 times 75, choose 8. 75, choose 8. Wow, that's a big number. Okay, I copy and paste. And maybe it does not want me to type comma. Okay, and divided by 100, choose 10. Okay, 100, choose 10. Okay, ooh, a big number. So, because here I couldn't find an online calculator with the regular calculation and the combinations together, but in your calculator, you should be able to type everything into one line and get it. So the answer I get is 0.2924. We round up. Okay, so 2924. We get 0.2924. So far, so good, everyone. Okay, so this is using the hypergeometric distributions. All right. By the way, when we compute the binomial distribution, I ask you to use the CDF to compute. So for geometric distribution and hypergeometric distribution, we use the PMF. So the formulas, okay, to calculate. Okay, so part B. Use binomial distribution as approximation. Okay. Okay, binomial distribution, what does that mean? Okay, we have 100 chargers, 25 of them are defective. So the probability of defective is like 25 over 100, which is 0.25. Okay, in this example, because we pick the chargers, okay, after we pick one chargers, there are only 99 left, and when we pick one more chargers, there are 98 left. So it's actually sampling without replacement. So, but if we use the binomial distribution to approximate, we kind of assume it's like sampling with replacement. So we just assume the probability of success in this case is 0.25 and use this to calculate. And then this is probability x equals to 2. How do we get 2? That's b of 2, and then n is 10, right? P is 0.25 minus b of 1, and then 10.25. Okay, and then now let's look at table 1. Okay, where is our table? So here n is 10, and then 0.25 right here. Okay, 2.5256. Okay, so those are my previous class. This is 0.5256 minus 0.2440. And what is that? Okay, let's see. 0.5256 minus 0.2440. We get 0.2816. They're kind of close. Okay? And actually, if the population size is getting bigger, then the binomial approximation is closer to the hypergeometric distribution. Okay, so in general, H, K, and Mn, okay, this is the PMF for the hypergeometric distribution. It approaches to the PMF of the binomial distribution with P equals M over N. Okay, so number of green bars over the total number of bars when the population size goes to infinity. So good rule of thumb, we can use the binomial approximation for n less than equal to n over 10. Okay, so in our example, you can see our n is 10 and our population size is 100. And then yes, 10 is less than equal to 10. So this is good. So that's why in our example, you can see the answer is kind of close. Okay, so this is a good rule of thumb. And usually if the problem wants you to use the binomial approximation, it will tell you to use the binomial approximation. Okay, everyone. So that is session 4.3. Okay, let's see. I want to give you one more examples. Okay, so let me type the example. Here is example 4. A small voting district has 101 female voters and 95 male voters. A random sample of 10 voters is drawn. What is the probability exactly 7 of the voters will be female? Okay, So let's see here what we're interested. The female we're interested, so we can define this is the success and probability. Let's see here because we have a finite number of populations, so that's why we use hypergeometric distribution. Okay, and here we have, let's see, we have 101, so this is M is 101. And what is male voters? Okay, and then the total is their sum. They get 196. And N is 10, we pick 10 voters, right? Okay, what is the probability that X equals 7? Well, here we have 101 female voters, and we pick 7. And then we have how many male voters? 95 male voters. We pick 3, right? And then we have what's the total? 196 voters. We pick 10 out of it. And what is this? Okay, you can use your calculator, the combination function, or you let me show you this online calculator. Okay, so let me move this. Oops, not this one. Okay, sorry, the wrong one again. Okay, this one. So first we want to find 101. Choose 7. And you can see this is permutation and this is combination where we need a combination. Paste times, and this calculator doesn't like comma, so we need to delete that. And 95, choose 3. So 95, choose 3. Okay. And then paste, delete the comma, and then divide it by 196, choose 10. Okay, here. Copy and let's see. Paste right here. So delete the comma. Oops. Okay. Do you see the answer is 0.130, we run up 4, so 1304. 0.1304. Okay. So this is the answer to example 4. And if you forgot like how to use your calculator to find combination, don't forget on our website you see I give you videos about how to use your calculator. Okay, so maybe let's watch this again, okay, together.
Hi everyone. So right now I want to teach you how to use your calculator to calculate combination. For example, if we have a hypergeometric distribution with the total number is 72 and like the number of green balls is 28, and we pick 10 out of them. Okay, so what is the number of blue balls? Well, that's the total number of balls, 72 minus 28, which is 44. What is the probability that the 10 balls we pick, we get 3 of them is green? So that is 28 choose 3. So all of these are combination. 28 choose 3 times 44 blue balls, we choose 7. And then 72 balls, we choose 10. Okay, so how do we put this in our calculator? So this is the calculator I use. So first of all, I need to put parentheses and 28. So 28, and you see I have this probability, and then I can choose combination. So NCR is combination. So 28, choose 3. So we plug in 3 here, and then parentheses. Okay, another parentheses, 44, combination. Choose 7. Okay, close the parentheses. Divided by 72. Choose 10 and close it. So our answer is this. So let me put it down. Okay, so our answer is 0.2341. So this is 0.2341. Okay, everybody? Next, if I want to find the probability x less than 2, so what are the possible values for x? It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Those are all the cases. So less than 2, it means it could be 0 or it could be 1. 0 means 24 green balls, we choose 0 of them. And 44 blue balls, we choose 10 of them. Okay, so let's calculate this. So 28 choose 0 is 1. Okay, so you don't need to put this in the calculator because it's 1. So how do we put it? Parentheses, 44, go down, choose 10. Close the parentheses, divided by parentheses, 72, choose 10. Okay, so this number is 0.004627. Okay, let's just put more digits down. Okay, how about the other number? The other number is, or you can just go up to the previous equation, right? You don't need to enter everything again. So now you can see I change my 7 to 9. Okay, and I change my 3 to 1. See? I don't need to type everything, so we just go up to the previous row and then enter it. So that can save us some time. So this answer is 0.037019. Okay, so we have this number, we add the previous number. Okay, so this is our final answer for this problem. Is 0.0416. Okay, and next digit 5. So far so good, everybody.
All right. So if you have any questions, feel free to ask me. Have a nice day. Bye.